So what I would like to discuss is the small world phenomenon, basically connectivity properties of random graphs. And so what I'm having in mind is, what happens if I draw two vertices uniformly at random? What happens to their distance? Well, the first most basic question is, if I draw two vertices uniformly at random, will they be connected? If they're not, well, or if they're not with very high probability, then somehow I have a very disconnected graph, and this is typically not what happens in real-world networks. So the question is, under what circumstances are we going to build a network that is actually highly connected? Huh? So that's what is called the phase transition. And for those of you who know something about the Erdős-Rényi random graph, it's very well known that if you take an Erdős-Rényi random graph and you take an edge probability which is like a lambda over n, at lambda is equal to 1, you see a phase transition. If lambda is larger than 1, you have a giant connected component. If lambda is smaller than 1, even at 1, you do not. Components are much smaller. The same is true for the configuration model. But the criterion under which it happens is a little different. So I did write this C max here with the bars around it. C max is the largest connected component. I'm assuming that it's unique. That's actually going to be true in most cases. The bars around it denote the number of vertices in it, so the size. And now I divide through by n. So that's the proportion of vertices that is in the largest connected component. This is very relevant because if I draw two vertices uniformly at random, independently from one another, the probability that they will be connected if there is a giant component is roughly this thing squared. So if this is not positive, I'm in trouble. Yeah? So what Molloy and Reed and later Jansson and Wuczak, Malvina Wuczak, did was to show that this proportion actually converges to a limit under my degree regularity conditions. And this limit could, of course, still be 0, but it's strictly positive precisely when a certain parameter is larger than 1, and this parameter is this object. The expectation of the degree times the degree minus 1 divided by the expectation of the degree. Now, in particular, when you have a power law which is in between 2 and 3, this value will be infinity. And therefore, your zeta will always be strictly positive. And now returning to your question, if I start with a very thinly connected scale-free random graph with a tau in between 2 and 3, this result will tell me that there is a giant component which contains a positive proportion of the vertices, because this object is infinity. But if I remove the highest connected vertices, a positive proportion of those, I could easily manage it in such a way that this nu will actually become very small. And then there will no longer be a giant component. So by removing a very small proportion of the vertices, you've destroyed the connectivity in your network.
So by basically having another configuration model where you just start kind of excluding them?
No, just taking this configuration model and just knocking them out.
Yeah. But
yeah.
Then you have like another configuration model where you rewire up.
Yeah, that's not what I'm having in mind. I'm really thinking about having the configuration model and removing the graphs, removing the vertices and all their edges. Okay. So this tells us when we should have a giant component. And of course, if we're interested in distances, this is the kind of setting that we want to have. So we will always be assuming that this value here is larger than 1. So it's either infinity or it's larger than 1. So there is a giant connected component. And then if we're talking about distances, as it turns out, there is a different behavior depending on the precise structure of your random graphs. So this picture that I was sketching with the British Queen and all paths going through that actually corresponds to a setting where the hubs play a very essential role. And in that case, distances are extremely small. If you don't have that, then distances are, well, they're small, but they're not so small. They're logarithmic. So for example, this is also the case for the Erdős-Rényi random graph. And there we actually do not really have vertices with extremely high degree. It's just that on the average you have more than one neighbor, and therefore this means that if you look closely around you, your neighborhood sort of is, at least in expectation, expected to grow exponentially. And because your neighborhood in expectation grows exponentially, after a logarithmic number of steps, you'll find the person whom you're trying to connect to. This is, of course, completely intuitive, and you have to, I mean, if you want to prove things, you have to do it differently, but it is the right picture. No? That's what this says. So, the distance between two uniformly chosen vertices, that's a random variable. Even when my graph is deterministic, this is a random variable. I look at this distance, I divide that through by log nu of n, where nu is this value, so nu is larger than 1, and you see that this is important here, because if nu is smaller than 1, you're in trouble. Then this would become negative. So nu is larger than 1, so this is some positive value, and if you divide through by this, this converges in probability to 1. So distances grow logarithmically in the size of the network. That still grows relatively slowly. Right? The log is a rather, it has a very strong effect on numbers. If you take a large number, take the log of that, it typically becomes a much smaller number. Yeah? But that effect becomes even more when you're in a scale-free setting with an infinite variance degree. In that case, it turns out that these distances do not grow logarithmically, but doubly logarithmically, log-log. And if you divide through by log-log, it converges in probability to a constant, which only depends on tau, on the power law. So in this case, distances grow doubly logarithmically. So you start from a large number, you take a log, it becomes a much smaller number, but still sizable. You take another log, it's gone. It's no longer infinite. Yeah? This is what happens. And there's some really peculiar aspects here, because I'm looking at one sort of asymptotic, right? I take this value and divide it through by something. This is like a law of large numbers. But instead, you could also look at fluctuations. So I look at hn and I subtract off log nu of n. Difference, of course, is much more subtle operation than dividing through. And you may wonder what happens then. Well, as it turns out, this difference is a tight sequence of random variables, as I say. So with very small probability, this difference is going to be larger than some large k or smaller than some negative k. Yes?
This reminds us what the difference between those two sets of conditions is 75.
Yeah. So I'll do that in the IID setting. So, theorem 1. You should think of, well, for example, this is a constant times k to the power minus tau minus 1, but tau is larger than 3. Alternatively, you could say that the second moment is finite. And in theorem 2, we have that the same condition, but now tau is in between 2 and 3. And that means, in particular, that the second moment is infinite, but even a moment slightly smaller than the second moment will be infinite. Yeah? So this means that the largest degrees are going to be much larger here than they are going to be here. So here the largest degrees are going to be larger than the square root of n. That's actually quite sizable. Much larger than square root of n. Whereas here they're going to be much smaller than square root of n. And depending on the precise behavior, so you could also have an exponential tail, as long as you're actually smaller or equal to this, everything is fine. So it could actually be an exponential tail, or it could even be a bounded tail. Random regular graphs would also be an example. Or it could be graphs that have a degree up to 100 but not larger. All of that would be captured in this. Whereas here you always have power law degree sequences with an exponent in between 2 and 3. That's a distinction. So here the role of the hubs, the high degree vertices, is much stronger than here. The hubs have degrees that are much larger. And you see that effect coming in the sense that because you have this hub structure that will actually shorten paths, this shortening of path is so substantial that distances, instead of being logarithmic, where you should think of around the vertex, you basically have a tree that grows. Here you also have a tree, but the tree grows extremely fast. And that's why you get these much shorter distances. Yeah. So what I was trying to say here was, if you take the difference, that is a tight sequence of random variables, so it remains bounded with high probability, but it does not converge in distribution. That's strange. So in probability theory, often when you have a tight sequence of random variables, we actually know there's a theorem, just like with bounded sequences. If you have a bounded sequence, there's a subsequence that converges. Okay? So for tight sequences of random variables, there's a similar statement. If you have a tight sequence of random variables, there exists a subsequence that converges in distribution. But it doesn't have to be. In fact, in this case, you do not have convergence. There is convergence somehow to a whole class of limiting distributions, and there's a continuum of those, and they're really different, and we can characterize those. So that's a bit strange. The reason is that the hop count Hn is a discrete random variable, and it actually tries to be close to the log of n, which is not integer valued. Now you can try to resolve that by taking a floor or a ceiling, but that still doesn't quite work because it really wants to be close to the log. And therefore you see that the fluctuations around the logarithm being an integer, they enter into your limiting distribution. So there is no limiting distribution. That's strange. And that actually occurs here as well. Yes?
With this doubly logarithmic with
Yep.
diameter, is there any particular features of this tree-like structure that is different from a normal tree?
Yeah. Yeah, there is. All right. How much am I going to say about this? Look at a vertex. Take this uniformly at random. So this could be the starting point of, this is the distance between two vertices. Two uniformly chosen vertices. Take the left vertex, so the source. You have a source and a destination. This is the source. Now you can look at the random variable z of k, which is the number of vertices at distance, graph distance, precisely equal to k from v. This is a well-defined object. For the time being, think of k as being fixed. Yeah? So this basically says, how many vertices can I reach with precisely k steps? And it's sort of obvious that this plays a role for this object. If you know how this grows as k proceeds, you know how many vertices you can reach within any number of steps. And this will also tell you, if you do this from two sides, when somehow these vertices are going to connect to one another. So it will tell you roughly what this size is. Okay? That's also how the proof goes. Okay? So, when tau is larger than 3, zk is roughly nu to the power k. So it grows exponentially. This is precisely what you're having in mind. Suppose that, one of the examples that you can have in mind is the setting where everybody has the same degree. Right? Now, it's very unlikely that you're seeing short cycles. So that means that if you don't have any short cycles, the number of vertices at distance k is precisely the degree times the degree minus 1 raised to the power k minus 1. That grows exponentially with k. Yeah? And this turns out to be true more generally, but typically what happens is that there's some limiting random variable here that somehow describes how things grow locally. Yeah? So you see exponential growth, and that actually immediately implies, because you see this nu here, that Hn is sort of the inverse of this in n. So Hn is the log nu of n. And that's precisely what you see there. Now, when tau is in between 2 and 3, this is actually not true. You grow much faster. So it's e to the power something that grows exponentially, because tau minus 2 is going to be in between 0 and 1, so 1 over tau minus 2 is actually a number larger than 1. So this number grows super exponentially, e to the power something times a constant. So this sort of says that Hn grows like log of n divided by the log of this value in absolute value. You have to be a little bit careful, because it should happen both from the left side and from the right side, and that's why you get the 2. Okay? That's the explanation. So what you see is, in terms of branching processes, this is a regular supercritical branching process. Supercritical branching processes that tend to grow exponentially. And this is a slightly less regular supercritical branching process, where the offspring distribution has infinite mean. And they tend to grow much faster. In fact, in many cases we don't know how they grow. But in this case we actually know that they grow like this. And you see that immediately reflected there. So what this means is that if I look at a random vertex and I look at its neighborhood around it, at a distance k for a large k, there's going to be way more individuals in the second case than there will be in this first case. Here there will already be a lot. Think of 10 to the power k, that's a lot. But here there will be 10 to the power 10 to the power k. Well, that's a lot more. So that's basically the idea. And just for those of you who ever do numerics, here you see the log. Okay, so you see that it tends to infinity, albeit that it goes relatively slowly. But you do see that it somehow, it grows. Ever more slowly, but still it grows. Here take the log. Now from my side I can see that it goes up. But from your side it looks like a constant. It's very difficult to see from simulations that log of x actually tends to infinity when x tends to infinity. I can give a proof, but that's not what you see here. Yeah? So if you take the log of 10 to the power 10, you're still somewhere at maybe 3.5. So maybe this is an explanation of 6 degrees of separation. Yeah? Yes?
I've got another question.
Previous theorem?
Yes. You mentioned this tight sequence that you get if you
Yep.
subtract log n from
Yep.
Hn. I wonder whether if you would subtract another fn, and this
No.
f might depend on the model that you're looking at.
No. Let me write down very precisely what we can prove. And I want to keep this, so I am going to go here. This, of course, is a very good question. I mean, the question is, are we actually normalizing in the wrong way? And I think our results show that this is not the case. So suppose I were to look at the following object. And I take the seal here, for example. Yeah. This is an integer, so I get an integer sequence. And now I take equal to k. Of course, I condition on Hn being finite. My graph is connected, I'm not conditioning on anything, but I need to do that. I can compute what this is, at least in leading order asymptotics, and it's going to be the probability that a certain random variable is equal to k, plus a smaller term, which vanishes as n tends to infinity. But this r of a depends on a, and an is the log nu of n, not rounded, minus the rounded version. So now I look at different n's. So this limiting variable actually makes a lot of sense. But whatever I do, this a of n as n changes will start hopping around in the interval minus 1 to 0. So that I'm not going to be able to fix that by changing, by subtracting something else here, because of course this still is going to be an integer. So this basically says that the limiting, well, not distribution, but the limiting set of distributions is this R of A, where A is in between -1 and 0. And that's what they are. And put this differently, for any A that you give me, I can give you a sequence of n's for which this law will actually converge weakly along that subsequence to that limiting random variable. So, I mean, this somehow answers the question, but it really shows that it's an unfixable problem. The problem really is there. By the way, this is a well-known problem with discrete random variables that grow logarithmically. This is a problem that you often see occurring. Another example where you see it is when you're in a situation, for example, where you're looking at the longest run of ones in an IID sequence of 0 ones with a probability p. Also, that tends to grow logarithmically. That's actually a theorem, I think, by Erdős and Rényi. And if you look at the fluctuations, the same phenomenon occurs. So you see this more often. Does that answer the question? Good. Other questions? Yes?
Is this like phase transition, or could you find graphs where you have hn is growing something between log and log log?
So for example, if you take tau to be precisely 3, then you actually get log n over log log n. And if instead of taking precisely 1/2 here, you have extra logarithms floating around, you can have log log n divided by any constant times log n. And personally, I believe that you can get anything in between log n and log log n by choosing the right power law with a correction. The correction has to be some sort of a slowly varying function, and depending on what the slowly varying function will be precisely, it will change the characteristics of the hop count. So for example, there are slowly varying functions for which the second moment still is finite at tau is equal to 3, and then you're still going to have precisely logarithmic behavior. That's one thing we know. But anything in between, I mean, this is something we can do, but I mean, there's a whole zoo out there in between log and log log, and we haven't been able to pin down that zoo.
Does this, I'm not quite sure, I mean, does this say that the diameter, I mean, in that case it says the diameter is log n over log n?
In this case, I think it is,
Yeah, it is
but
in that case,
I don't think that there is a proof for that.
Okay, this doesn't prove the diameter of these things.
Well, I'm wrong here, by the way. If in this case you have a positive proportion of vertices of degree 2, the diameter will be log.
Okay. Yeah, so it doesn't.
It really depends on the precise characteristics of the degree sequence.
So it says more about the average distance.
Yeah, this is the average distance. So if you look at the diameter of the configuration model, you divide through by log n. This will converge to a limit. You have the same term that you also see appearing for the graph distances, not the diameter, but there is an additional term. And this additional term will be positive precisely when the probability that the degree is less than or equal to 2 is strictly positive. So the thing you should bear in mind is that if you have a positive proportion of vertices of degree 2, you can actually create a very long string of vertices that only have degree 2. And the halfway point, well, that will have a distance to anything else that is at least half the length of this line. And the longest line that returns us to this longest sequence of runs will be logarithmic. Now, if your degree can be 1 with positive probability, but not 2, you have to update this argument, but it's still the same order of magnitude. Yeah? But this term vanishes when the degrees are all at least 3. By the way, this result is also true when nu is infinity. Then this term just vanishes. So then the average distance is log log, but the diameter will be log. And this is realized by very thin paths that have a logarithmic length. But of course, you cannot have very thin paths when the degrees are all 3, because then every point is somehow expanding, at least exponentially. So you cannot not have anything so thin. So what happens then is that when tau is in between 2 and 3, and you do have vertices with degree 2, the diameter will be logarithmic. But if the degrees are all at least 3, the diameter will also be doubly logarithmic. It's larger than the average distances. There's a little bit added to it. this somehow comes from points that are extremely thinly connected, the thinnest possible. That means that all these vertices have the minimal possible degree. But still, this can be quite large, and you're somehow not growing this super exponentially as you would otherwise. So it really changes something to the diameter. But there's very detailed results for these kind of random graphs. Any further questions? So in the direction of universality, so I presented 3 theorems for the configuration model. The first was about the phase transition, is there a giant component? And the second 2 were different behavior for different values of the degree distribution for the distances. And I will now go through the same steps, but then for the generalized random graph. And after that, I will do the same for the preferential attachment model. Okay? So the first result says something very similar to what we've seen for the configuration model, and it says that there is a giant component. So this is the phase transition for the Ehlers-Danlos random graph, for example. If I look at the largest connected component, look at the number of vertices in there, divide through by n, then this converges to some limiting value, denoted by zeta. And this limiting value is strictly positive when a certain nu is larger than 1, where nu actually is the expectation of w squared divided by the expectation of w. And w is this limiting weight of a uniform vertex. Now this formula looks a bit different from the formula that we were seeing for the configuration model, but actually it's the same. And why is that? Well, this is phrased in terms of the weights and not in terms of the degrees. And remember, I've shown a result that says that if I look at the proportion of vertices with degree k, this converges to a little p of k, and that little p of k is the expectation of e to the power minus w, w to the power k divided by k factorial. That, of course, is the same as the expectation that a Poisson random, the probability that a Poisson random variable with random parameter w is actually equal to k. Yeah? So the degree is a Poisson random variable, but I need to stick a random parameter into that. So if I then look at the expectation of d, well, that's the same thing as the expectation of a Poisson random variable with w. The expectation of a Poisson random variable with a parameter lambda is lambda. So this is the same as the expectation of w. Okay, that's nice. If I look at the second factorial moment of the Poisson distribution, well, it's well known that if you look at a Poisson random variable, the expectation of the Poisson random variable times the Poisson random variable minus 1 is the parameter squared. So this is nothing but the parameter squared, but the parameter is w. So I get the expectation of w squared. So if I look at nu, and that was by definition, the expectation of d times d minus 1 divided by the expectation of d, that's the same as the expectation of. So they're the same. No? That's the whole point. So this at least suggests that there is a clear relation between these different random graph models. And this relation is actually a lot deeper than you might imagine. I already mentioned that if you look at the configuration model and you condition on simplicity, meaning no multiple edges, no self-loops, then what you get is a uniform random graph with the right degree sequence. That is a theorem. Now if you look at the generalized random graph and you condition on the degree sequence, you also get a uniform random graph with that degree sequence. Now, of course, the degree distribution is a random sequence. But still, if you condition on it, so you're conditioning on lots of things, you're again getting the same uniform random graph. So that means that you have the following equalities in distribution. So if you look at the configuration model, and you condition on the configuration model being simple, that has the same law as the generalized random graph with a proper weight distribution, conditionally on the degrees being, the degree sequence being that same degree sequence that we see here. Okay? Because they're both uniform random graphs with the right degree sequence. Okay? Now suppose that I know a result for the configuration model, then I know that the probability of being simple is strictly positive and converges to some value. So the conditioning is actually relatively harmless. So if I know something for the configuration model, the same result will be true for the configuration model conditionally on simplicity. Okay? So suppose I know that, then if I know, so of course here I need to make assumptions on the degree sequence. If I know that the degree sequence in my generalized random graph satisfies these assumptions, so the degree regularity, then I will actually get the same result for the generalized random graph for free. This is the reason why we're actually starting with these configuration models under what may look like a little bit strange conditions. I mean, you could just say, well, you know, take these degrees IID and then we're done. That's fine if you want to think of it that way. But if I want to prove something for the Erdős-Rényi random graph, and I already have the result for the configuration model, if I can show that the Erdős-Rényi random graph satisfies these three conditions, that's actually not very difficult, then I get it for free. I don't have to do anything. So this explains why there's so much relations between the behavior in the configuration model and the behavior in these generalized random graphs. And also why we're phrasing these results in this way. Okay, so these results will then not come as a big surprise. Actually, you see the same behavior for the degrees, or for the distances, under the same conditions, namely nu needs to be larger than 1, the expectation of w squared needs to be finite, and then hn grows like log nu of n. That's the same as what we saw before. And if we have a tau in between 2 and 3, then the distances grow like log of n. And you have the same limit. And this sort of explains why you get these same results. And you have similar extensions for the diameter, for the case where tau is equal to 3, etc. All right. One more model to go in terms of small world behavior. The preferential attachment models. Now, preferential attachment models are really different. They're really much more difficult. And the reason that they're much more difficult is that they evolve dynamically. Now, what I would like to do is I want to draw a vertex uniformly at random. So that means that it has a random age somewhere in between 1 and n. But this age is extremely important. If I know that it's the first vertex, I actually know how many neighbors it has. But if it's the 100,000th vertex in my graph of size 100,000, then it will actually have no degree whatsoever. So, and it's this age that makes it very difficult. So if you want to keep track of vertices, you need to keep track of their age, but then also the age of the people they refer to and the age of the people who refer to them. So it becomes very complicated. And this is the reason why we can actually not prove as much for the preferential attachment model as we can for the configuration model. In a certain sense, it's much less homogeneous. There are some really nice results in a slightly different model by Peter Mutters and Stefan Derreich and their collaborators. So I'll tell you about the results that we do know. Let m be greater than or equal to 2. If m is 1, we're building a tree, right? A vertex comes in, it has one edge to give, it connects it to whoever is there, you get a tree. Depending on whether you allow for self-loops or not, you're going to get a forest or a single tree. So it really depends very sensitively on the precise rules. But when m is greater than or equal to 2, it turns out that after a random time, your model will be connected forever after. That's what this says. I mean, it's a dynamic process, so the time at which you see this connectivity or disconnectivity, disconnectedness for the last time is going to be a random variable, but there is a finite random time after which the preferential attachment model will be connected forever after that moment. That's actually a fairly strong statement. So this is very closely related, if you bear in mind, I mean, m is at least 2 here, but that means that if you take a vertex along a path, there's one edge coming in, and then there's 2 edges coming out. So somehow all the important vertices have degree at least 3. So there's a similar result for the configuration model if you assume that the minimal degree is at least 3. And that says that actually the configuration model will be connected with high probability if the minimal degree is at least 3. And for that you don't even need degree regularity. You basically take anything you like. When the minimal degree is at least 3, with high probability the graph is going to be connected. It's quite nice. For 2 it's not true. All right. So that's the connectivity. Now how about distances? Well, in a certain sense we were having tough luck. Because there's an old result by Bolobach and Reardon, who investigated the Albert-Barabasi model for the very first time, and they immediately also investigated the diameter in this model, and this turns out to grow log over log log. But this was for tau is equal to 3. We had all these results for tau unequal to 3 for the configuration model, but not the result for tau is equal to 3. And now we have the result for the preferential attachment model for tau is equal to 3, and none of the other results. So checking universality is a bit difficult, because the sets for which we know the results were completely disjoint. They covered everything, but... So there was a later result that showed that for the configuration model we have the same behavior, also log n over log log n, even with the same constant. That's interesting. And for the other results, if tau is greater than 3, we don't have very precise results. The problem is just a lot harder. I mean, it is true that we believe that there should be some sort of a branching process in the background, and this branching process should grow exponentially. So you should have some logarithmic behavior with a sharp constant, but we have no idea what that constant should be. What we can show is that both the diameter and the pairwise distances between uniform vertices are bounded below and above by constant times log n with high probability. It's just that the constants are different. So it's at least, let's say, 1 over 1,000 times log n with high probability, and it's bounded from above by 1,000 times log n, also with high probability. So it grows logarithmically, but we don't have very precise control. When tau is in between 2 and 3, the situation is a little bit different. There we do know that the graph distances grow like log log n with a precise constant, and the constant even looks a lot like the constant we were getting for the configuration model. But it's a factor 2 larger. That's a bit strange. But that's what it turns out to be. So for the configuration model we had precisely the same result, but here there was a 2, not a 4. So it took us some time to understand what the difference was, and let me try to explain that to you. So if we look at the configuration model, and tau is in between 2 and 3, I was indicating that if you look at a vertex, and if you look at its local neighborhood, it grows extremely quickly. And the way how it does that is, you start from a vertex which has a bounded degree, because it's just a random vertex, and it goes to neighbors that have a higher degree, and those go to neighbors that even have a higher degree, etc. And what you see happening is that the highest degree vertex in somehow the shell around you at level k actually is a positive proportion of the total number of individuals. So you're basically growing by each time taking a vertex with higher and higher degree. And this higher degree grows super exponentially. So that basically means that if you look at a path, and this reminds me of you'd have 2 uniform vertices, you take your path, So the degrees here will be bounded. They will actually converge in distribution to some finite values. And here they will grow larger and larger and larger up to the middle point, where they will be largest, and then it will go down again. And actually the degrees along the shortest path will grow super exponentially. So you should really think of the queen as being here. The middle point. This is this vertex with a gigantic degree. And what you see occurring here, so let's say after a few hops you're already looking at vertices with extremely high degree. So here and there you have two vertices with a very high degree, and they're connected to one another directly. Now that's not the picture for the preferential attachment model. So also there you see that vertices with a very high degree play an essential role, but they play a different role. And that's because of the dynamic nature. So the vertices with very high degree, they come into the game relatively early. It's the old vertices that are very rich. The old get richer model. So only the old vertices have very high degrees. But they are not necessarily connected to other old vertices. Definitely not all of them. So what a path looks like in the preferential attachment model, when tau is in between 2 and 3, is it looks really differently. You start at two uniform vertices. Well, we know what the degree distribution of that will be. They will be finite again. And now you somehow slowly walk up, but every time you go down again, you go up, you go down, you go up, you go down, you go up, you go down. So there's a parity effect. So here, the vertices, the degrees are growing super exponentially. But two vertices with very high degree, so here you have a vertex I of n with very high degree, and here you have a vertex j of n with very high degree. They're not going to be connected to one another. But what is true is that there's going to be a third vertex that connects to both of them. So if I compare that picture to this picture, what it means is that if I want to go from vertices with high degree, there will be a distance 1, and here there will be a distance 2. So the distances are twice as large. So that's why you get a 4 here, whereas you get a 2 in the configuration model. That's it. So discussion. We quantify the small world behavior. We look at these different models. They behave in the same way. So if you give me a tau in all of these three models, you will see the same kind of behavior. So for the configuration model, the generalized random graph, or the preferential attachment model, if tau is larger than 3, distances grow logarithmically. If tau is in between 2 and 3, distances grow doubly logarithmically. So that's universal. It's a universal aspect. A downside of this model is that they're locally tree-like. So if you look at a vertex and you look at its neighborhood, that neighborhood will look like a tree. Now that's not true in reality, particularly in social networks. So if you look at an individual, you look at their friends, many of their friends will actually be friends of one another. So what you see is lots of small triangles of people who all know one another and are all friends of one another. That's not part of these models. So these models really should be considered to be a caricature of reality. But caricatures of reality can be useful and also fun in order to understand what is happening in the real world. If you really want to use these models for real-world applications, you'll have to do something else. And this is the literature on the configuration model and for the inhomogeneous random graph and the preferential attachment model. And that's it.